Good morning, everybody. Well, I hear some polite British folks in the front responding correctly. Let's try that one more time. Morning. Good, that was much better. Okay, let's start with the introductions. I'm knackered. That's not actually my name. It's merely my state of mind right now. I've done quite a few of these sessions and I am extremely tired. For those of you that don't know what knackered in British means, it translates to devastatingly tired. I went bowling last night and when I tried brushing my teeth this morning, the toothbrush made it to there. I had to lean forward for the rest, so I'm feeling my age. Anyway, I'm Dean Wells. I'm a program manager in the Windows Server base team. I own a good chunk of Windows Server technologies, especially in the area of security. Things like our Host Guardian service, shielded virtual machines, and pretty much the overall security story for the server product itself. With me, I've got Mike from NIST, the National Institute of Standards and Technology. Mike's going to come up and talk about a reference architecture that they've got put out there into the wild for the government agencies as well as enterprises to leverage that's built on Microsoft security technologies. And I've got Jakob Smashed. No, I've lost it, Jakob. I'm sorry. We'll just leave it. Jakob from the SQL team. Anybody want to try that last name for me? Very good. Somebody from your hometown. Okay. So, Jakob's going to be talking about a brand new technology that's going to be released in SQL 2019 called Always Encrypted. I will tell you that the reason he's on stage with me is because he and I have been working on this project for 2 years, I think, something like that, back and forth, making sure that things operate the way that they're supposed to, the way they're supposed to. It runs inside something we call a trusted execution environment, or an enclave. Who's heard of the term enclave? Quick show of hands. Who's heard of the term SGX enclaves? Okay, SGX is a platform technology by Intel that is meant to provide a trusted execution environment on a machine that could be literally littered with malware. And yet the trusted execution environment is able to defend itself from inspection, writes, modifications, all those kind of things. What we've done in Windows Server 2019 is we attempted to build a similar technology to that, which we achieved. The security promises are not as strong as an SGX enclave, but we call it a VBS enclave, or Virtualization-based Security enclave. So you're going to see a demo from Jakob that talks about how they're leveraging that technology in SQL 2019 with their Always Encrypted offering. All right, so without further ado then, let's just set the stage, some context. We've obviously got a number of IT stress points right now. You see the two at the right, data center efficiency. This is a big deal for most, as is supporting innovation, i.e. staying close to the trend, keeping up with the technology evolution. The one that we're going to focus on is going to be about security threats in this session. There are 3 areas that we like to break this down into. The managing of privileged identities. If anyone knows a little bit about my background, you may have seen me at Ignite before, or back in the days when it was called TechEd. I have a very strong identity background. Managing privileged identities is one of the biggest deals today, whether it's on premises, whether it's in the cloud, or in some hybrid situation. Hence the introduction of technologies like Azure MFA, the multi-factor authentication. How many of you are subject to multi-factor authentication now when you log on to sensitive services at work? I know I am. Okay, good. That was the vast majority of you. The other thing that started to become more prominent, it's not really around privileged identities, but it's around devices. How many of you are now seeing your devices have to comply with certain policies before you're allowed to use them to access work data? That's again true at Microsoft. Okay, so that is starting to become more pervasive. All of that, if you bucket into managing privileged identity, it's all the same thing. It's just the identity of the device this time, not the identity of the person using it. And in an ideal world, it's both. That's pretty much the way Microsoft works. The second thing we'll be discussing is how do we secure the OSs? Most of the platform technology in Windows Server that went towards security, that's going to pretty much take up the content I'm talking to you about today. These are things that you don't really get to see. I said this the other day when I had to follow Cosmos Darwin. Fantastic name that, isn't it? I wish my parents had called me Cosmos Darwin. There really is no better name than that. It's not even a stage name. He was really born with it. I had to follow him after doing a presentation on disk performance where he showed millions upon millions of IOPS being satisfied by an S2D array of these brand new types of storage called, I think it's NVMe, I can't remember what the rest of the acronym is. And it went so ridiculously fast for so many virtual machines and so many hosts. He managed to get a round of applause from the audience just by virtue of the number. And then they asked me to come up directly after him and talk about security. Good. So how do you make security a wow moment? By showing nothing bad happening. Isn't that it? That's what Windows Server 2019 focuses on. Thank you. Look at that. I got a round of applause for showing nothing at all. Okay. Next, secure fabric virtualization and actually leveraging those virtualization technologies for the purpose of security. I'm also very heavily into shielded virtual machines, which is an offering on Hyper-V. We'll talk about that because we're trying to get the message out there. I did a session yesterday that I will sort of plug at the end so you can go and watch it on video that talks about the attack vectors against virtual machinery merely by virtue of the fact that they are running as a VM instead of on bare metal. So it's a rather interesting session. We'll do some of that in here. So let's talk about some of these numbers. This is for real. I think the biggest one there is the $3 trillion. So $3 trillion annually. Impact of some kind of cyber attack. $3 trillion annually. That is a massive amount, and this data is now about 18 months old. So it's growing all the time. When you see these numbers, it gives you an idea of just how bad a problem this has become. Here's what we refer to as our attack timeline. This is not one of our proudest moments, especially this piece here. We've no idea how long it takes them in research and prep, but we do know that once they've got the research and prep down and they've got that first entry point, the average is 24 to 48 hours to go from entry to domain admin. How many of you know what the prominent means of achieving that were? Pass the... There it is. Okay, well, as of 2 days ago, we had solved the pass the hash problem with something called Credential Guard that uses virtualization-based security technologies to prevent the components that were reaching in to LSA, the local security authority's memory, stealing the hashes, and then using them to authenticate and impersonate significant identities. And I said as of 2 days ago. I saw a potential breach of that. It looks like somebody may have found a small window in time to reach into Windows and steal the ticket. I don't know if it's true yet. Obviously, our own MSRC folks are looking into it and trying to get a reproduction. I haven't seen confirmation either way. If we do find some kind of avenue of attack, we will be investing, obviously, a massive amount of time, energy, and resources in terms of devs to get this one fixed. But Credential Guard leverages these same virtualization technologies I'll be talking about later to try and prevent those attacks. And it's been successful since the launch of Win 10 and Server 2016. And it's only now that somebody may have found a very microscopic window in time to go in there and get it. But it is a window in time. It's probably going to be far less than like a tenth of a second. I'm going to say it's probably going to be way less than that, but we haven't seen all the data yet, so I'll keep an eye on that. Anyway, the idea here is to give you an idea of how long these people sit inside your network. So this mean dwell time, 146 days. That's pretty scary. That's to the point of detection. So you don't know what the research and prep was. They hit domain admin by 48 hours, and then they sit there for 146 days, exfiltrating whatever the heck it is they want. The domain admin credential is not the gold, right? That's the means to the end. They don't want that credential. It just buys them access to anything else. So we've worked very, very hard over the past decade or so to try and address this situation, and we have. We've made that a significantly longer time frame from the 24 to 48 hours. And with Credential Guard, we'd almost rendered it infinite, but now obviously I have to take into account what I learned a few days back, and we'll see where that lands. What we also learned is there's something that almost every attack has in common, and it is the section that we're in. If you take a look at it, when we merge all this, we get admin privileges. Every attack seeks out to exploit these admin privileges. We actually discussed in Windows removing the concept of an admin, removing the very notion of this all-powerful administrative account. That lasted about 12 seconds. We laughed and moved on. I'd love to say we can do it, but how can we do that? How can we change the management paradigm? How many people would adopt that? And the reality is, I don't think people would be able to because it would break so many existing scenarios. We eventually decided it wasn't really feasible. All right, so here are the principles that we build on. The reason I bring this slide up and I put these 4 pillars is to make sure you guys realize we don't just go and build random, arbitrary security features in the hope that it makes something cohesive. We are actually following a set of principles. And if you look down the bottom, security is not a bolt-on to us. It is an architectural design principle, something that should be there from the very beginning. So take a look at some of these lessons. I think the top 2 are the most interesting for me. Read that top one. I want to see who agrees. What this is basically saying is, in the past, we used to invest massively in securing the perimeter of the network. You had to VPN in and all these good things that sort of measured the health of your machine. Was it running anti-malware and all that good stuff? Microsoft no longer invests like that in perimeter security. Of course, we have some. But when I first joined Microsoft, if somebody sent me a link to source code and I tried to read it at home in Outlook Web Access, I either had to have that machine running some special agents, it would then need to use direct access over a VPN. None of that anymore. As long as my machine complies with the health policy, as long as I comply with the standard credential authentication process and then the multi-factor aspect, it will bring up source code for me. Why would it not? If it's proven my machine is healthy and it meets their policy, and it's proven I am who I say I am through at least 2 forms of authentication, then why not show it? So the perimeter is no longer where people are investing. They're investing at the endpoints, and to my mind, this makes more sense. If you implicitly trust everything inside your network, then the obvious thing for an attacker to do is focus everything they've got on getting 1 foot inside and then moving laterally throughout it. So there's a brand new initiative that's been instigated by one of our security guys over in a team that we call Enterprise and Security. He's calling it ZTN, or Zero Trust Networks. I'll reference a blog about that in this slide deck so you can go and have a look at it. They're building technologies that will allow you guys to deploy things like Zero Trust Networks, where you trust nothing about the underlying network carrier. The physical cabling and the switches, all those components, they're not trusted anymore. In that way, we build the protections all the way in at the network layers and right the way down to the endpoint. So this is a good initiative. It's a good wave to go forward, and we've just started building the products to allow folks to implement that. All right, so protect, detect, respond, and isolate. These seems like good areas to attack. Obviously, in the protection case, we're talking about technologies that prevent tampering. So we didn't necessarily detect it, but the malware tried to do something malicious, and we had code in place that blocked that from happening. Virtualization-based security is one way that we do that. In the detect camp, that's things like Windows Defender and a number of other components that are new, System Guard, Runtime Monitor being them. And then obviously we've got response and isolation, and I'll talk about each of these as we move through. So this is the only way I can imagine of conveying every single thing that we've got just in these painted down boxes, because if I speak about every single one individually, we're going to be here all day. Just-in-time admin, this is a way of ensuring that the privilege you carry is only sufficient for the job you're doing at that point in time. So if you're browsing the web, ideally you do that on a generic workstation with a low privileged account. If you're going to administer Active Directory or some sensitive workload, a PKI server, those kind of things, then you should really JIT up, it's become a verb now, just in time, or JIT up into a more privileged account, and ideally be doing so on a privileged access workstation. Who has privileged access workstations at the office already? Okay, so for those of you that don't, go onto the internet, go to Bing, go to gubing.com and search, I'm going to buy that website for those of us that can't quite change. Go to gubing.com and search for the term privileged access workstation or secure access workstation. This is another industry initiative where we're simply saying that people need to use workstations that are health attested. They are measured very carefully for health. And if they are not healthy, they will be unable to administer whatever workload it is they're supposed to administer. This is yet another fantastic initiative. Microsoft is very heavily into this. So there's a whole slew of features in there. The AAD banned password list. This is not actually in the code of Server 2019, but it's released around the same time frame. This is written by the Azure Active Directory team, who also own Windows Server AD, and it takes some of the artificial intelligence and very, very clever matching techniques that Azure AD uses in the cloud and brings them on premises into Windows Server AD. It does clever stuff like looking for medial string token matches. So you might do a massive password like this, but it notices that there are repetitive phrases inside it, or perhaps it even has a reference to your company name. No, that's not good enough. It also uses clever algorithms, something like the, I think this is referred to as the Levenstein distance algorithm, which is the number of character changes that occurred between the current password and the new one. And the idea is that if you only changed it by one, a slight iteration from one to the other, on a particular string that it's looking for, then it's going to consider that as insufficient. But not as a blanket statement. That by itself is insufficient. But if you had extra padding at the front that looked very unique and at the end that also was unique, then it will allow that one through. If it wasn't, then it will block it. So this is now available for download. We also did a session that had a demo with this, and it was Jeff Woolsey's session, which was, I think, Windows Server 2019 Deep Dive. I did a 5-minute demo on that walks you through how to install it, where you get it from, all of those good things. So like I said, the list here just goes on forever. There are so many components now in the platform, but they're not all set up for you. You have to make the proactive effort to go and get some of these things. Even with virtualization-based security technologies, we can't just switch them on carte blanche because they have a performance impact. And there are other things that will stop working. For example, when you turn on virtualization-based security, video drivers that use dynamic code creation, where they literally morph their own code in memory for genuinely legitimate purposes, that won't function with virtualization-based security and hypervisor-enforced code integrity. It simply isn't allowed. You can't update code pages when hypervisor-enforced code integrity is on, and that requires VBS. So we can't just arbitrarily turn these features on. You have to be proactive. You have to make the decision, do I take the pain of the video driver not working and get the vendor to fix it? We've obviously applied a huge amount of pressure, and in my opinion, most have now done it. But it does still require you to make sure that you test these capabilities out before doing so. Securing the OS, this is probably the area where we invested the biggest. Device guard, code integrity, that is the hypervisor enforced code integrity. The reason I keep emphasizing the hypervisor piece is because in the past we used kernel to enforce code integrity. Kind of logical, right? But what if we wanted to enforce code integrity against a driver that runs in kernel mode? Okay, well now we need something lower in the platform. Well, most copies of Windows, depending on how you've got them configured, don't boot the kernel first. They go through an OS loader after having a handoff, a secure handoff from UEFI firmware. And then at some point down that binary chain, the hypervisor comes in very early. And the hypervisor starts managing the hardware, and the rest of the OS is subject to the hypervisor's whims. They cannot access the hardware. They have to ask the hypervisor nicely. This gives us a place to lay these new policies. So if we put code integrity policies there, then the hypervisor could even block things that a malicious kernel was attempting to attack. That's the reason that we design stuff this way. Control flow guard. Has anyone heard of CFG? 1, 2. Okay, so 2 out of roughly 1,000, I would say. This is one of those platform components. It is buried way down in the weeds of the product. In Windows 10, some of the older releases, we had user mode CFG. Now we have kernel mode as well. What is CFG or control flow guard? The idea of this is it's there to try and keep applications and binaries, runnable code, on the rails by preventing them from being attacked, where, for example, somebody tries to get them to run out of a natural sequence. So rather than running in the natural sequence of the binary as it exists in memory, somebody tries to make it jump to a different location, execute out of natural sequence, and potentially reveal a secret by virtue of doing so. And believe it or not, these are now well-known attacks. So we have CFG in the platform now, built in. You never really see it. It's also built into Visual Studio since it works better when the compiler can actually give hints in the binary to CFG as to how it should be running. Again, I'm not sure that there's another operating system out there with these technologies in the platform, but it makes Windows 10 and Server 2019 the most malware-resistant technologies out there. And then we start talking about things like Defender ATP. It's in the box now. Anti-malware, antivirus, and anti-ransomware for free, mostly. Come on, we're in business. But they are incredibly capable technologies. And the reason that we decided to encroach on this market isn't because we wanted to put anyone else out of business, but who better to write the technology that protects the operating system than the operating system vendor? If there's a kernel API that gets in the way of a third-party anti-malware tool, what do? Work around it. What do? Well, I walk 2 corridors down, I go and ask Ben to fix the API. Okay, that's way more successful and far easier. So that's really why we started this. We want the product to be secure straight out of the box. If you look down here, we split into host and guest, a hardware root of trust. People are still running legacy BIOS, the PCAT or PCAT as we call it. The security that provides you in terms of a root of trust is precisely 0. The boot path of PCAT is this. It runs the BIOS. There is no integrity check. It then looks for the first boot disk in sequence, grabs a 512-byte sector of code, and runs it arbitrarily. Okay, what if that 512-byte sector of code had been put in place by a rootkit? It's now been redirected. It runs my rootkit, then redirects to the real one, and now the rootkit's sat there watching everything else that's going on. You can't detect that with PCAT. With UEFI, we look for signatures. We do not permit handoff from the firmware to the OS loader until the signed image on that OS loader, the signature, is measured against a variable inside UEFI called DB. We look for either a hash or we look for a code signing certificate match. And then we also look in DBX, the exclusion list, the blacklist if you prefer, to make sure that that binary isn't in the blacklist. It hasn't been excluded as well. If you are not running UEFI firmware, I encourage you so much to do so. Everything else that Windows does after that is rendered somewhat moot if you do not have a root of trust that is rooted in the hardware. It is absolutely fundamental to keeping these security guarantees. And then what we started doing is we do the same with our guests now. We give them the ability to leverage virtualization-based security techniques that are inherited from the host. So if the host is rooted in hardware, and then we start projecting virtualization-based security technologies into the guest VM, we've now got a chain of trust so that even the virtual machine itself is trustworthy. We've even built things like synthetic TPMs to ensure that we can work on that front as well and make guest operating systems as secure and operate in the same way as their silicon counterparts do. Last but not least, secure fabric virtualization. This is where we've got shielded VMs that are resistant to malware. They're resistant to malware, and they're resistant to host admin attacks on the very host where they're running. That is the goal of a shielded VM. Protect itself against malicious activities on the very Hyper-V host that it's running on. Hyper-V containers, I'm sure you've seen container sessions. There have been about 10 or 11, I think, so I imagine you've been into those. We've got micro-segmentation with our software-defined networking. That's what SDN stands for. SDN now provides encrypted subnets so that applications or workloads that don't use secure technologies like SSL, for example, or TLS, or any derivative, we now encrypt the subnet for you with inside the software-defined network, so even insecure packets on the wire are automatically encrypted. And last but not least, we added 802.1x support into the vSwitches in this release as well, which a lot of people are extremely happy about. Last but not least, we obviously have monitoring solutions that paint themselves across everything. Some of them are hybrid, some are directly on-prem, some are exclusively in the cloud. So let's talk about some of what's new then. The sum of what's new starts with our shielded VM improvements. Who has ever used a shielded VM or deployed a shielded VM environment? 1, 2. Okay, I guess we got about 10 there. We're trying to make that a little bit more of a representative number. People use Hyper-V, people use VMware. We understand that. People are not protecting those virtual machines, which is why I want you to watch that session to see what the attack vectors are and just how crazy bad they are. Shielded VMs set out to protect themselves from attacks from the host. That's their goal in life. Not attacks in the virtualization plane. That's the job of the existing software that we've been working with. Take a look at what we've done there in terms of what OSs we support. We now do shielded Linux. It was the biggest ask. As soon as shielded VMs came out for Windows, the biggest ask was, give us shielded VMs that support Linux. That is now available in Server 2019, so you can now run shielded Linux VMs as well. Device guard policies. This is that hypervisor enforced code integrity I mentioned. In Server 2016, if you changed the policy, you had to reboot. With Server 2019, we gave you a policy in the same policy, in the HVCI policy, that says whether I can apply new policies without having to reboot. So the HVCI policy can say, I allow additional policies to be applied without a reboot. If you didn't have that and you then applied it, what would you have to do? Reboot. And now additional policies can be applied thereafter. You can also stack policies now with Server 2019 so that you can author one policy for one thing, another policy for another, and then add them together to create one effective policy. Kernel control flow guard, we already mentioned what this is there for, to keep binaries on the rails, run as they're supposed to. System guard runtime monitor, this is one of my favorite new features. This actually beats SQL to the punch. This runs inside a VBS enclave. This is, if you like, the first Microsoft solution to run inside an enclave. Jakob's disappointed now. He thought he was first, but no, this was there before him. This is there in Windows 10 already. The idea is it sits there and it watches the watchers. It watches Defender ATP. It watches that VBS is switched on, Virtualization-based Security. It checks that you've got CI policies. It checks a number of different things. It then generates a report based upon measurements inside the TPM, which it sends off to the cloud. The cloud looks at the legitimacy of that report and tries to make a decision as to whether it's accurate or whether it's been tampered with, again, by using the TPM. It then signs the report and sends it back in the form of a token, which has claims inside it that indicate the health state of this machine. So it's a JOT token that has key value pair claims in it. One of those is called sec level, or security level. If your security level is 0, that means you are literally nothing as far as System Guard Runtime Monitor is concerned. You have no security. If you do not have a TPM and you are not using UEFI firmware, you will get a 0. On a decently configured Windows 10 machine today or Server 2019, you'll get around 300. What it then does is it passes that up to Defender ATP. So Defender ATP in the cloud can actually consume this token from System Guard Runtime Monitor wherever Windows may be running. It could be in Azure, it could be on-prem, it could be in VMware, it could be in Amazon, in Google. It doesn't matter where it is. It will still go up to our cloud. What Defender ATP will do then is make an assertion of trustworthiness based upon that report. So we're now actually taking a signed report that was cloud attested with Defender ATP, making an assertion of trustworthiness and feeding that into Intune. Intune then for client machines at least, not for Windows Server. They don't manage Windows Server, they do the client side, but System Guard Runtime does exist there as well. They pass that along to Intune, who makes a decision based on compliance requirements. Do you now meet the compliance as well as the trustworthiness bar? And if you do, we feed that into Azure Active Directory. Azure Active Directory then, when asked to give a token to gain access to a sensitive resource, is making a decision based upon who you are, what Intune thought of you compliance-wise, what Defender ATP thought of you trustworthiness-wise, and what System Guard Runtime Monitor actually measured in the running machine. How cool a scenario is that? This is one of the contributing technologies to this whole thing I mentioned earlier of zero trust networking. So take a look at this. Look it up on the internet. There's a nice blog. I've got the blog documented in here as well. It'll give you an idea of how this stuff works. So can we use hardware capabilities to redefine the Windows security guarantees? Yes, absolutely we can. Take a look what we've got here then. If we go through the list, we want to make sure all code executes with integrity. Nothing can be done, we hope, to tamper with it. We've got technologies in place now. Nothing is a bit too much of a blanket statement, right? We do our best to ensure that nothing can be done, to tamper with the natural execution order of the binary. User identities cannot be compromised. We talked about that. That's the privileged access stuff. Attackers with casual physical access cannot modify code or data or liberate it. There was an issue where Thunderbolt devices, you would plug it in and it could start liberating control of the machine. There was a little USB stick that pretended to be a NIC, and then it added a DHCP server on the end, and Windows started sending it confidential information. All of these things, this casual physical access, we've put controls in place. Malicious code cannot persist. That's obviously Windows Defender. It finds something malicious, it removes it. Violations of these promises are observable. System Guard Runtime Monitor. We made a promise about code integrity. Some malware switches off hypervisor enforced code integrity. Who spots it? System Guard Runtime Monitor does, because it's running inside a trusted execution environment called a VBS Enclave. Last but not least, all apps and components have only the minimum bar privilege that they need. So here are the technologies that we talk about with code execution. This is where Control Flow Guard and hypervisor enforced code integrity reside. And please feel free to come back and review this deck afterwards. It's written to stand alone, i.e. without me providing a voice track. It's written for you guys to learn from it. So hopefully you'll take some value from it even after the fact. We already spoke about this one. Casual physical access doesn't provide the ability for you to literally just liberate data or start making changes to code or data on that machine. Violations are observable. We've got tamper-evident windows now. We want to know when Windows is being tampered with. That's why we had to build this trusted execution environment. Because if we cannot trust the piece of software that is trying to spot the tampering, then what's the point? So read up on what we did with VBS Enclaves and the security boundary guarantees that we will make around this. This is a strong piece of software, and it's a huge step forward for overall platform security. Again, though, it's one of those things where if everything's working as it should be and it's doing its job, you see nothing. Makes the wow moment a little bit difficult, but that's what we're striving for. So there's the blog that I'd like you to read. It talks about zero trust networks, and System Guard Runtime Monitor is obviously one of those. And obviously you guys will get a copy of this deck as soon as you like. You can download it from the Ignite site. All right. Let's see if we can transition over to Mike now. Mike's going to talk to you about the reference architecture that they've built on shielded VMs, guarded fabric, host guardian service from the National Institute of Standards and Technology. So over to Mike. Thank you very much.
Thanks, Dean. Great job for being completely knackered. So like Dean said, my name's Mike Bartok. I'm from NIST, the National Institute of Standards and Technology, and part of our cybersecurity portfolio, we have two main goals. One is to develop standards and guidelines for best practices for the federal government to use. And the other mission that we have is just kind of with the work we've done with Dean and his team is part of our National Cybersecurity Center of Excellence. That's to go out to different vertical industries, have them define cybersecurity challenges to us, and try to build reference architectures to achieve solutions to those problems. So what this project that we're working on is called Trusted Cloud. And so what we're trying to do is build on top of some of the capabilities Dean mentioned at a high level, like trusted hardware, the fabric-based technology to help secure hypervisors and virtual machines so that people can adopt the cloud at a quicker rate. So the way the output of these projects works is there's a NIST special publication 1800 series document that we'll publish. It consists of 3 volumes. Volume A is a high-level executive summary. So this is, you can take to your C-suite and tell them, you know, we want to adopt the cloud. We want to do it in a trusted manner. This proof of concept architecture might help us achieve that. So it'll have a high-level overview of the project, the challenges we're trying to overcome, and the solutions and benefits to what we're doing. Volume B is the approach, architecture, and security characteristics. So kind of does a deep dive into the challenge, the specific security outcomes that we're trying to achieve, and includes a reference architecture of how we're building out the solution to this problem. And it will also do a mapping of security controls that we're achieving to the NIST cybersecurity framework and 853 control family. That way, your CISO or your security admins will know what kind of compliance requirements you're meeting by adopting the solution. And Volume C is a really technical how-to guide. It shows every step that we went through to actually implement the solution. It'll give you screenshots or pointers back to, for instance, Microsoft's installation guides. To actually, you could pick this guide up and go replicate the work that we've done. So this specific instance of this project is called the Trusted Private Cloud Project. We've collaborated with industry partners for this build. Dell's providing us hardware, Intel's providing us processors, Microsoft's providing a bunch of software, and we're also working with Docker and Twistlock on top of this as to run inside of our VMs. And so what we're doing is we're taking what Dean talked about in the hardware trusted attestation, as well as virtualization for guarded fabric, to be able to build out trusted hardware that you can run workloads on top of inside of the shielded VMs that Dean touched on. So we're trying to meet 6 main security outcomes within this project. One is deploying hardware roots of trust technology so that we can, as Dean talked about, measure the hardware, firmware, and operating system that our workloads will be running on top of. So we're leveraging UEFI and TPMs to do measurements of the servers that will be running Hyper-V, so that on each subsequent boot after we provision them, we know that nothing has changed, nothing's been tampered with, and so we can still trust that hardware. And the second foundational security outcome is actually being able to deploy virtual machines to those servers and make sure they can't be deployed to untrusted servers. That way you know your workloads are running exactly where they should be. And on top of that, we're building on additional security objectives, such as encrypting virtual machines before they're deployed. So when you want to deploy a virtual machine, it only gets the decryption keys released to a trusted server. That way you know an untrusted server can't run the workload. We're meeting least privilege principle for network flow. So as Dean touched on, we're leveraging Microsoft's software-defined networking to apply micro-segmentation policies to all the virtual machines. So if they move from one server to the other, you know that this micro-segmentation policy will still apply to it. So for instance, if you migrate one virtual machine, a web server, to a different host, it still will only be able to talk to an application server. It can't talk directly to a database server based on the policies that you define with SDN. We're also trying to ensure industry sector specific compliance. This will actually help you adopt this, and as you adopt it, map how you're meeting your compliance, your regulatory compliance. So we're using Docker and Twistlock to help do that. As on our workloads, you can define what sort of information they should be running. You can measure what the Docker images are and make sure that they're deployed. So if you have a HIPAA compliant image, when you deploy it, it stays HIPAA compliant. You can do scans to make sure that no configurations have changed, so you're still meeting your industry sector compliance. This quick slide just to show how we're going to map everything, as I mentioned, to the NIST cybersecurity framework and 853 controls. That way you can start, as we build this out, this mapping of how we've installed everything will be mapped to these controls, so you can see how it will meet different industry regulations. And here's just a very high-level architecture slide. We have three different planes or zones that we have 2 zones, 3 planes within each zone. Each is a different geolocation zone, and within that, each 3 planes are the same. We have a management plane, which will run a host guardian service from Microsoft, which will actually be the attestation server that all the hypervisors will talk back to. So each time it boots, it does it gets an attestation report from the TPM on each server to make sure that the firmware, the BIOS, and hypervisor are still in the same state that it was before and still trusted. We have domain controllers running in there as well as CAs, so we can provision certificates to each server to make sure that it can meet some sort of trust policy. In the compute plane, we're running Hyper-V as our hypervisor, Virtual Machine Manager to do the management of everything, SDN, the software-defined networking, to define and deploy those microsegmentation policies, and also another server with shielded artifacts on it, which helps you be able to deploy shielded VMs, which Dean will talk about in a little more depth to talk about what kind of security advantages they give you. And within our workloads, we're running Docker Enterprise Edition, which gives you a single pane of glass view of your container images across both zones. It has something called the Docker Trusted Registry, so you can sign container images and only have signed images deployed as workloads, so that you know that it's gone through a rigorous development lifecycle and has been signed before those images can be deployed. And then Twistlock will actually do the vulnerability scanning of of all the Docker images, so you can make sure that there's no active vulnerabilities within images that you're running. And will also help you go through the configurations on each VM so you can make sure that they're still meeting your industry-specific compliance policies. So this is just showing how each one of these security outcomes or security objectives are being met by each of our partners within our NCCOE. We have Intel, Dell, and EMC helping do the hardware root of trust. That's the measurement of the hardware, firmware, and hypervisor, so that you can attest to it each time it boots to make sure the hardware is still trusted. Microsoft is doing the orchestration for deploying virtual machines. They're also helping do the encryption of virtual machines so they can be decrypted only on trusted servers. Microsoft and Docker are helping with the network segmentation. We're using, like I said, Microsoft SDN to do microsegmentation policies, as well as Docker network overlays on top of that. And then Twistlock will help meet industry sector-specific compliance. Quick status update on this project. We pretty much have all the hardware deployed, most of the Microsoft services deployed and configured. As part of this, it's a partnership with all these different vendors. So each vendor, Microsoft, Dell, Intel, they're providing all this hardware to us and engineering time. So we've been working closely with the Microsoft engineers to have the Host Guardian service deployed, SDN configured, and we've finished doing that. We have Docker EE installed and Twistlock installed as well. So to finish this up, we need to connect our 2 trusted zones that I showed you, so we can do a migration between each zone from trusted host to trusted host, and then configure Docker EE and Twistlock to make sure everything's working together, and then publish all of this. The way we're publishing all of it is we're doing each volume in series. So we'll publish our executive summary very soon, I would say by the end of this quarter. And then the volume B, which is the high-level architecture, should be soon after that, the very beginning of 2019. And then volume C, which is the actual how-to guide, so anyone could pick this up and replicate the work to do the installation, will be probably in the first or second quarter of 2019. And at the bottom of the slide is a link so you can read more about the project and get status updates as they occur. So with that, I'll kick it back over to Dean to talk about the virtualization infrastructure security.
Great, thank you very much. All right, so a lot going on there. The amount of documentation that comes out of these sort of exercises is mind-blowing. Mike knows exactly how much documentation because he writes a good chunk of it. But this is the way in which enterprises are going to start to deploy this. So I think we're right on the verge of seeing this become a commonplace deployment model, which is exactly what we want. So let's talk about virtualization infrastructure security. For those of you that attended the Shielded VM session yesterday, this is going to be similar in some cases, and I'm going to go into a little bit more detail. The idea of this rather amusing slide is that for many, many years, the majority of the industry, Microsoft included, had their head in the sands regarding protecting virtualization infrastructure itself. Workloads got all the love, the endpoint got all the love, but if you deployed it as a virtual machine, nobody did anything to stop an admin walking off with a VHDX or a VMDK. And if I walk off with a VHDX of a domain controller, give me 10 minutes and I'm going to have all the hashes I need. That's a scary proposition. Try doing that with a physical domain controller. We have doors and padlocks and gates and security guards and all those good things. And in England, we have truncheons, and over here guys have guns. Or, it's a different thing. It works, though. We seem to manage quite well. The point I'm making is, if you do that with the virtualization host, you still haven't secured everything. What you did is you secured the virtualization host. The guest VMs are just artifacts residing on it that can be reached remotely. I can copy the entire VM definition off. If I can do that without anyone's knowledge, I can then spend an unbounded amount of time attacking it until I get something useful. We have to put protections and controls in place to prevent this from happening. So if you take a look here, a customer runs a VM. It could be you guys. You run a VM on a host, even in your own enterprise. Do you know from within the VM if the host is healthy? The answer is no, obviously you don't. With a shielded VM, you do. Do you know how you know? Because it's running. That's literally how you know. There is no way the host could have executed the VM. It wouldn't have been given the key. It was measured too thoroughly. That's the idea behind shielded VMs. And eventually we'll start putting, I hope, signals into place that you can pull down from the hypervisor infrastructure to get some kind of claims that would attest to that. All right, so a guarded fabric then. This is just a term. This is not a technology. Hyper-V, running many instances of it, that are being attested by a host guardian service, that is what constitutes a guarded fabric when it's running shielded VMs. So what I want to do is I want to show you some of these security assurance goals that we set out for. We want to ensure that the VM's data is encrypted at rest and in flight. We want to ensure that the key release strategy adheres to what the industry has decided is goodness. The key release strategy is something I encouraged people in yesterday's session to ask as a question every single time, because it's far too easy for vendors to say, oh, it's encrypted, therefore it's protected. The cipher, that helps, but the key release strategy is the important piece there. If the key is stored in a file on a file system directly next to the asset it protects, then what use is the encryption technology? So if you don't ask that question, it could be rendered entirely moot. What is the securest key release technology that is commonplace available? TPMs. TPMs work by measuring things. As the system boots, it measures stuff. I'll give you a quick sort of 25-second walkthrough as to how that measurement occurs, because it's rather interesting. So power on a brand new machine, any of your laptops. It's probably got UEFI firmware inside it, and it's probably got a TPM. Once the UEFI firmware is loaded, and it's built on top of a base firmware from Intel called Tiano Core, and then there are vendor-specific extensions. That's kind of an assumption that that's trustworthy. We do the best we can to keep that Tiano Core-based firmware trustworthy and in a trustworthy state, and so do all the vendors. Dell, HP, Lenovo, they're all doing the best they can to ensure that their firmware is trustworthy. It has secure variables that contain code signing signatures, or hashes, or both, of what it considers to be a trustworthy loader. And it contains the opposite of that, a blacklist. So then once the UEFI firmware has done its stuff and the devices are initialized, it goes looking for the OS that it's going to hand control off to. And it examines the OS loader and checks the signature on that OS loader to make sure that it complies with something that is listed in DB, database of goodness, and something that is not listed in DBX, database of badness. As long as that is true in both cases, you're not in DBX, and in some way you are in DB, it will take the OS loader and hand control off. Now Windows is in control, or Linux is in control. What we then do is we measure every single binary. And by measure it, that means we take some kind of cryptographic measurement of it, typically a hash, that we then store inside a component inside a TPM, a trusted platform module, called a PCR, or a platform config or control register. These hashes that go in there are representative of one binary. So then we hand control to the second binary. But how do you create a chain of trust where you've now handed control off to a second binary? Well, the first binary actually knows what the hash or the signature is of the second binary, or at least the code signing cert, which is more typical. Is the second binary in sequence signed by Microsoft? Is that sufficient? Is it present? Yes, it is. All right, I will hand control to the second binary. We then hash it again. We've now got two hashes, right? We've got the first binary, which is in a PCR, and we've got the second binary hashed in memory. So we take those two strings, and we add them, and they become one big hash, which is now too long. So we hash it again. And then we put that back in the PCR. And guess what we do with the third binary? We check the signature. We hash it. We concatenate that hash with what's in the PCR. Hash it again, put it in the TPM. By the time you're done, you have a very, very statistically unique hashed representation of a known boot path based upon the UEFI firmware, a trusted OS loader, and a sequence of binaries that ran in the correct order. That's how TPMs work. At the point the OS is up and running, components seal keys to the TPM based upon a set of measurements across various PCRs. It could be PCR 7, 11, and 20. And then they'll seal a key to that. And what do you think the TPM validates when somebody says unseal the key? It validates that the PCRs are in exactly the same state of health. If they are, that's when the key is released. That's how BitLocker works with TPM-backed key protectors. That is a key release strategy. Putting a BEC file on a disk is not. Putting a BEC file on a USB key that is kept in a safe, okay, you're getting closer, but it doesn't implement anything to do with the trustworthiness of the binaries, it just gives it the key. This is the way in which things should be done. We do that both on the Hyper-V host for guarded fabric technologies, and then we repeat it again inside the VM because the shielded VM has a VTPM, it has UEFI firmware. The same thing happens in both the guest and the host. That's how we meet that top goal. Now, that was obviously a rather lengthy explanation, and not every bullet's going to take that long, I hope. All right, so fabric admins are locked out because the keying material used to encrypt the VM's file system is BitLocker's full volume encryption key. They don't have that. It's inside the TPM. The TPM is encrypted by keys that are held on an external attestation service. Malware is blocked because attestation of host health is required. If the malware is running and it caused the measurements to change, what do you think is going to happen? If the measurements changed, we don't release keying material. Enterprise private cloud. So the idea here is you can put a sensitive workload straight inside your Hyper-V guarded fabric cluster of machines, and it may achieve a compliance bar merely by virtue of being shielded. For example, PCI, the payment card industry, if you've got a workload that today runs only on bare metal because virtualizing it would cause you to fall into non-compliance, run it in a shielded VM. Compliance brought straight back. I'll show you the compliance assessments that we had done after the fact. This is not just hearsay. This is an actual third-party company that did the compliance assessment for us. Public cloud, obviously we want to have shielded VMs up there and running in Azure. We're now working on Gen 2. So once Generation 2 VMs are available in Azure, the next step would probably be VTPM, and then after that, we'll start looking at the full shielding capabilities offered in the public cloud. Branch office scenarios. How many of you struggle with deploying sensitive workloads like domain controllers to branch offices? Okay, I know I always did. If you don't struggle and you just do it, that doesn't mean you're right. You're supposed to be struggling with this problem. If you do put a domain controller in a branch office, where does it run? Oh, it's underneath the secretary's desk running on a regular tower. That's horrific. That literally means somebody could run in there, run around the back of the desk, walk off with it, just unplug, rip all the cables out, and now they've got a domain controller that provides passwords that are relevant way outside that branch office. Logically, then, if you can secure that machine in some way that requires it to reach out across the WAN to a centralized data center to have its health attested and measured, that would be a great way of doing it. Shielded VMs do that extremely well. So they are very, very useful for deploying things out in branch offices. So rather than putting one machine there as a domain controller that you're a little concerned about, put a single Hyper-V host there, run a domain controller and whatever else you need, and that machine is measured and attested by a data center across the WAN. People said that that was a great idea, but they were concerned where they were deploying these things in environments where the WAN was fragile, like New Zealand, for example. I don't know why I picked on the Kiwis there, but whatever. Anyone from New Zealand in the room? Okay, so yes. Oh, there is. Damn it, I was going to really go off on them. I can't now. So let's say that there's a fragile WAN in New Zealand between the data center and the branch office. Actually, isn't New Zealand a branch? It's just the whole thing is a branch office. Sorry about that. I've completely lost my train of thought now. All I've got is insults from New Zealand in my head. So if we consider the branch office scenario to be somewhat troublesome, if we've got machines that run out there or VMs running on Hyper-V hosts that are shielded, we need to ensure that we don't inadvertently create a denial of service attack by not allowing the keys to be released to those hosts. If the WAN has gone down, and it went down because the rest of the network went down due to a catastrophic power failure, they try and boot the machines back up, and now the shielded VMs can't be booted because the Hyper-V host can't reach the host guardian service. Uh-oh, nightmare. So in Server 2019, we added additional technologies to the guarded fabric. One is to have an alternate host guardian service, rather like you have a preferred and an alternate DNS. It's the same sort of mentality there. And the second is we seal the keying material to the TPM of the Hyper-V host, so that if it is down in terms of the WAN, and it can't reach its alternate host guardian service, as long as its boot measurements and all of the security things that were measured remain consistent with the last time it was deemed healthy, the TPM will unseal the keys locally, allowing the shielded VM to come up. If anything has changed, rootkit, a patch that was not properly signed by Microsoft, if any of those things have changed, then the security of that system, the measurements will have altered, the TPM will refuse to unseal the key, and justifiably, the shielded VM will fail to start. That's the desirable outcome in that state. Something is wrong with this host. It's not the same as it was when it was last measured healthy. And you can turn on this caching, this offline mode, as a host guardian policy. So these are all the things that we've been doing to try and make these scenarios realistic. Sorry, Sarah, about the New Zealand references. My apologies. There goes my reviews. So what do you need, then, to make a guarded fabric? Well, you need this. Shall we dig into every single one? Let's not. So if you look at it, this is quite literally everything that's in there, and I'm missing some because I ran out of space on the slide. Forward secrecy, synthetic TPM, secure VM provisioning, external health attestation, hardware-based root of trust. This is all part and parcel of a guarded fabric. We leveraged some percentage of these and had to build the rest from scratch. So, shielded VM security model. Let's give you an idea of how the health attestation works. So, on the left, we have a cluster of Hyper-V hosts calling a guarded fabric. On the right, somewhere nice and secure, we have the host guardian service cluster. You'll notice there's a flashing key. The key in the host guardian service is what is required to power on the flashing shielded VM. So the first thing that the host says is, hello, I'm host 1, can I have some keys, please? And the host guardian service responds with, not yet, I need to verify that you're healthy, so just go with the traditional cough. It does so. It then sends back, yep, you look good to me. Well, exactly what happened there. I'm going to do this as fast as I can. So for the non-English native speakers, you might want to record this and play it back slowly. The first thing we do is we have to harvest something called an endorsement key from the TPM of the Hyper-V host. That is its immutable identity. It's called an EKPub, the endorsement key public. It is not a domain joined secret. It is a hardware immutable key that comes out of the TPM. We register that with the host guardian service. The Hyper-V host then powers the shielded VM on and goes, oh, I haven't got the key. Give me the key. No, I won't give you the key. Attest. Okay, here I go attesting. Here's my EKPub, the endorsement key public. That goes over to the host guardian service. The host guardian service looks at it, compares it to a whitelisted database and goes, yep, I recognize you. At which point, it makes up a random symmetric key. So it computes a new symmetric key. It encrypts that with the public key that just identified the Hyper-V host. Remember, public keys are used to encrypt things. And what do we then do? We send it back to the Hyper-V host. If there's any malware running on that Hyper-V host, can it read it? Nope. Only the TPM can decrypt that. We also pass that key into VBS, the Virtualization-based Security Trusted Execution Environment. The TPM decrypts the key in there, and it's now got a symmetric key. Step 2, attest. Show me what you did when you booted. All of those measurements I told you about where we extended and added, concatenated, hashed again, stored it down. That's the process that we're talking about here. That is also written in series into a file called the TCG log, the Trustworthy Computing Group log file. That records the sequence of events in terms of the binary sequence, while the TPM creates cryptographic representation of that sequence of events. So we send the TCG log up, which is signed. And we encrypt it using the symmetric key that the host guardian just sent us. The host guardian takes it back, decrypts it using knowledge of that symmetric key, looks at the TCG log, and it goes, yeah, that looks good to me. But what if the machine was lying? What if there was malware on it and it somehow managed to lie? Well, what we do is we recompute what the PCRs should look like in the TPM. We recompute what those PCRs should look like. Then we reach back over into the Hyper-V host and we tell the TPM, give me PCRs 11, 7, 20, whatever a set of PCRs we're sealing to, and it sends back those PCRs across the secure channel. If we computed the same thing as is stored in those PCRs, which are known to be trustworthy because we trust TPMs, then the machine has now told us who it is. It's now securely communicating with us using a very, very short-lived symmetric key. It's told us what it did when it booted, and we've validated that its TPM agreed with it. We then compare that against the whitelisted policy, and we go, yes, you look good to me. Last but not least, we take a good thorough look at its hypervisor-enforced code integrity policy to make sure that malicious admins or malware have not changed it or deleted it. So yes, we even measure the hypervisor-enforced code integrity policy. Only then can the machine say, all right, I've done all that, I've got a health certificate. Here it is. Can I have my keys now? At which point, the key gets sent back over, goes inside the little virtualization-based security enclave, at which point the shielded VM can now be decrypted and powered on. So, when somebody says that certain competitor technologies known as encrypted VMs are comparable to shielding, why don't you go back to that former slide and ask them which of those they have, and do they do anything like this? I think the answer is going to be no, but I don't spend all my life looking at the competition, so maybe I'm wrong, but I'm fairly confident that's quite unique. So what did we do then? We now support all of these releases of Linux. That was a fantastic step forward, and it was not easy. This was not a trivial thing to do, but we've got it running. Native protection of the root and boot volumes using dencrypt, which is the equivalent of BitLocker, I guess, for most Linux distros, and secure provisioning workflow is fully supported. The only thing we can't actually do is we can't convert a non-shielded Linux VM into a shielded one. We can do that with Windows, we call it grandfathering, but with Linux shielding VMs, you have to deploy them from scratch. Host key attestation. This is a new way for you guys to deploy shielded VMs using an incredibly simple attestation technique. It is not thorough. It is not using the TPM. It is there for you to test. Does the shielded VM work for the rest of my virtualization fabric? Do I find those guarantees healthy? Or perhaps you trust your admins and your fabric, and all you really want is a decent solution for data at rest encryption and on the wire. This would work for that. The process of guaranteeing a machine in this model is go over to the machine, run a commandlet on it, it produces a key pair, copy it over to the host guardian service, and input it. That's it, you're done. None of the TPM identity, none of the measurements are in place. You are merely authorizing, not attesting to the health of. But it does allow you to test the rest of the shielded VM workflow to make sure it doesn't encroach on anything that you want to do or block it completely. Branch office support, we already discussed that one. This is precisely how that looks. So on the left there, that's New Zealand. On the right is... Gentleman's going to hate me. On the right there is the main data center. Where shall we have that? Let's be really rude. In Australia. There we go. So shielded VMs improve troubleshooting. We had to add back some features here, which we were loath to do, but people told us that blocking VM Connect and PowerShell Direct for shielded VMs in its V1 incarnation was too much. So we had to relinquish our controls a little bit there. So we now permit VM enhanced console connections, which require the OS to be running, require you to authenticate, and they leverage RDP. We do also permit PowerShell Direct now. So you do have ways from the Hyper-V host now of talking to shielded VMs, but it does require you to authenticate to the guest machine. In the first release, neither of those were possible. Okay, last but not least, we also now support this. This is a huge deal. We've had customers asking us for this for years. We never supported it in the vSwitch, so if the vNIC inside the guest VM was mapped into directly a vSwitch as opposed to a physical LAN adapter, you couldn't do 802.1x. Now you can. That's built into Server 2019. So there's the summary of all of the things that we did in Server 2019 with regard to shielded VM improvement and general network security. The list is pretty extensive, and I would encourage you to give it a shot. At this point, I'm going to hand over to Jakob. Last name again, please? No? Who could? Oh, say your last name.
I'll do it.
Okay, he's going to introduce himself because I'm clearly a moron. So over to Jakob.
Right. Thanks, Dean. Hi, everyone. So the name is Jakub Szymaszek, and I'm Program Manager in SQL team. I work on security features for Azure SQL Database, SQL Server, and I'm here today to share with you how we are using some of these exciting innovations Dean talked about, including VBS Enclaves and Host Guardian Service, to deliver some truly game-changing data protection capabilities in SQL for our SQL customers on-prem and in the cloud. So many of you are probably familiar with technologies for protecting sensitive data at rest or in transit, like transparent database encryption that we have had in SQL Server for years, or SSL, TLS for protecting sensitive data in transit. Now, the type of protection that has been missing until recently is protection of sensitive data in use in database systems. By that we mean the data that is being used for query processing inside the database system, right? And that's a problem that the technology that we introduced in SQL a couple of years ago called Always Encrypted is trying to address and solve, okay? So what we want to achieve here is we want to protect sensitive data that is being used during processing of SQL queries inside the SQL Server process from high-privileged but unauthorized users. That includes potentially malicious DBAs, machine admins, rogue cloud administrators, or anything bad that may be running on the machine that is hosting your database, right? We want to make sure that these potentially the malicious entities, these powerful adversaries, cannot access your sensitive data in plain text at any point of time. So the challenge here is that it's very hard to do without compromising the data processing capabilities of the database system, right? So what we ideally want, we want to protect sensitive data in use without sacrificing, without compromising the SQL Server ability to support rich computations, rich queries, right? So what we really want is we want the database system to support rich operations, rich computations, without exposing the data to, in plain text, to potential adversaries. In other words, what we want SQL Server to do is to reason about the data without seeing it. So as you can suspect, this is quite hard to do, but we have these innovations that make this, solving this problem now possible. And the key technology here is secure enclaves. So let me explain quickly what a secure enclave is. So an enclave, and Dean briefly talked about it, is basically a protected region of memory in a containing process. And it's a region of memory with some special cool properties. Namely, it's essentially a black box, not just to this containing process, but everything else that is running on the machine. Even the operating system cannot access the inside, the internal memory of the enclave, right? And Dean also said that there are multiple ways to achieve this isolation. Some technologies achieve that via hardware, and Intel SGX is an example of that. But what I want to focus in my presentation here is what Windows team has done in Windows Server and the new version of Windows 10. Namely, there is this technology called Virtualization-based Security and VBS Enclaves, right? So here is an idea of what you would see if you would attach with a debugger to a process that contains a VBS enclave, right? Even if you're an administrator, what you're gonna get are these question marks, right? You're not gonna see the memory of the enclave. So the hypervisor, what it does, it acts as a guardian of this enclave memory, and basically it rejects any attempts to access that memory, right? So that makes the enclave an ideal environment for processing sensitive data, right? An ideal execution environment for processing queries on sensitive data. And that's exactly what how we're using enclaves in SQL Server. So let me explain what we have done with that. So about 2 years ago, we shipped this technology called Always Encrypted in SQL Server and Azure SQL Database. And what it does, it's a client-side encryption. It basically ensures that any data that leaves an application and targets the database gets encrypted inside a client driver. So as a result, the SQL Server, the database, never sees the data that it receives in plain text, right? So now we are extending this technology by leveraging secure enclaves. So now when SQL Server process starts, it will load and initialize a secure enclave. And this enclave will act as a logical extension of the client application, as a logical extension of the client-side trust boundary, right? So now what we can do, the SQL Server during query processing, it can delegate computations on sensitive data to that secure enclave it contains, and that enclave can safely decrypt the data, and now having access to plain text, this enclave can perform some rich operations on the data, like pattern matching or range queries, right? And it can also do in-place encryption, in-place cryptographic operations. So without enclaves, if you want to encrypt a column, if you want to rotate a column encryption key, for example, in your database, and you have a large data set, you need to move all the data outside of the database and move that encryption elsewhere. With Enclaves, we can do these kind of operations in place. Similarly, if you have an application that needs to perform rich operations on the data, without the Enclaves, you need to move the data outside of the database and re-implement the business logic in your application. With Enclaves, all that can be done in place locally inside the Enclave. So that's what we want to achieve here. Now, so you may ask a question. So I just told you that this Enclave acts as a trusted ally of the client application on the server side, right? But how does the client really know that this Enclave is trustworthy, right? And this is the problem that we are solving with, among other things, Host Guardian service. So let me walk you through that process quickly, and I might need to ask Dean to help me out here for a moment. So this is what happens. So the client application submits a query to the driver like adu.net or ODBC, JDBC, right? And the first thing that the driver does, it will actually reach out to SQL Server telling the server, show me a proof that the enclave that you have is actually trustworthy, okay? So the first step that SQL Server will do to produce this proof is it will reach out to the Host Guardian service, which is expected to produce what, Dean?
A health certificate. So you saw this earlier on. The exchange between the SQL host and the Host Guardian service here is exactly the same as the exchange between a Hyper-V host, just to get to the point of issuing the health certificate. So all of that stuff with the EKPub, the computing a symmetric key, securing the path, decrypting it, taking the TCG log, that trustworthy computing group log, signing that, verifying that that computes back to the PCR state, and then finally measuring the hypervisor enforced code integrity policy, which Jakob doesn't like. They don't actually have a need for that piece, so they measure it to the point of it's not there, is kind of the piece they do. It's not really necessary on a SQL host. Once that's done, we finally send back a slightly different form of a health certificate. That then goes all the way back to the SQL host, gets shoved inside the VBS container, and then the VBS enclave kicks back off and does whatever it's going to do next, which is where I hand back to him.
Right. So after that, we have the health report. So the next thing that the SQL Server does, it calls the operating system on this machine that now has been certified, if you will, by Host Guardian service to produce what is called an enclave report. And it contains the information about the code that is running inside the enclave, among other things. Then all this data is sent back as a response to the client. And now the client starts the verification process of that proof that was provided by SQL Server. So it calls Host Guardian service to get the public key that AG assigned that health report with, and that is used to validate the health report. And now it knows that the host machine that produced the enclave report can be trusted. It verifies the signature of the enclave report, and then it looks at things like the signature of the code running inside the enclave, or it verifies that the enclave it doesn't run in a debug mode, which would mean that the developers could actually peek inside the enclave and see its content. That's not all we want. So now let me show you a quick demo of Always Encrypted with Secure Enclaves as an illustration what we have accomplished here. So for my demo, I'm going to use a very simple database with just one table that contains information about employees. And as you can see, some of this information is fairly sensitive. Government ID numbers, social security numbers, salary figures, right? And I also have some web application that presents all that information, okay? And there are some UI controls here that allow me to filter all the data by, for example, salary range or social security number. Now, every time I use this UI, this application issues a SQL query. So let me show you, using my extended event monitor, how this SQL query actually looks like. So this is the query that the SQL Server gets, right? So you can see here, this is a fairly rich query. It contains a like predicate pattern matching operation on the social security number. It contains a range comparison on the salary figure. Okay, so this is what we want to do in this demo. So we want to make sure that high-privileged users, DBAs, for example, or machine admins, cannot see that sensitive data information, salary figures, SSN in plain text. On the other hand, we want to make sure that after we protect the data in use, this application can remain unchanged, can continue running, and these rich queries at issues like this one continue run, and SQL Server can process that, right? So we have these two goals that we want to reach. So let's do that by enabling always encrypted with secure enclaves in this environment. So one thing I want to show you quickly, luckily, my SQL Server instance is running on a machine that has been configured as a guarded host, as a guarded machine by HDS. And here's the information of my attestation service that the role is played by HDS. So now I can encrypt my data, my sensitive information, by simply running a SQL query, which will trigger in-place encryption. I want to show you one thing here, which is now I'm acting as a owner of the data. I need to make sure that I have access to the keys. I need to make sure that I configure my tool that will be encrypting the data with the proper information. That includes the link, the endpoint of the attestation service, because this attestation workflow we walked you through would be kicked off the moment I start this query. So let me do that.
1 minute. 1 minute.
1 minute. We're almost there. All right, so I have my data encrypted. And how do we know it's actually encrypted? So that's what I could see before when I ran this query as a DBA. I rerun it now. The data is encrypted in these two columns, right? So now, for a very quick moment, let's go back to our web application. And it still works, right? Not only that, the cool thing is that these filtering capabilities also work. And if I show you the queries, how they look like now, I guess that doesn't refresh. But okay, now you can see it. The query stays exactly the same. It's the same rich query. So I have my data encrypted, protected in use, and I still can run rich computations on the data inside SQL. The only difference you see now is that the data, the query parameters, the search criteria SQL Server gets are now also in the encrypted form. So the SQL Server sends the encrypted query parameters, encrypted data to the enclave. The enclave decrypts both, performs required computations. So we achieved both goals that until now have been mutually exclusive: encryption in reuse and rich queries. Cool.
Great.
Thank you.
Thank you very much.
Right.
I can tell you that that looks really, really simple, because when security works, it's supposed to look exactly the same as it was without it. But the amount of effort that went into this from our respective teams is mind-blowing. It took us a long time to make this work. Okay, compliance mapping and summary then, just to wrap up. I mentioned to you earlier that shielded VMs will provide you PCI DSS compliance merely by running a workload inside them. There are also some other things that we've put compliance effort into. This is a third-party compliance attempt here. They're the ones that do it. It's not us biasing. They independently assess these capabilities against our product, and then we'll walk out the door with a PCI DSS 3.2 or some other compliance bar merely by running it inside a shielded virtual machine. This is what it looks like, so you get some really good detail there. Here are the related sessions that I would wholeheartedly recommend you go look at. The confidential computing one starts in about 30 minutes, because Jakob and I are going to go and do that now. I'm hoping it's not too far. No, it's not. That's handy. Secure virtualization, that was the one that we did yesterday. Go and watch that. It's a 45-minute session. It goes extremely deep into a series of attacks, even going as far as using a crash dump to go through and examine memory to try and steal full volume encryption keys from VMs and a Hyper-V host. So it goes from the simplest of attacks to the most complex. There's the blog I mentioned earlier with regard to System Guard Runtime Monitor. That is one of the best components that we have conceived of and implemented in the past few years, as far as I'm concerned. Extremely clever idea and implemented brilliantly. That contributes to Zero Trust networks. And then obviously we've got demo videos and a variety of different blogs for you to go and have a look at for additional info after the fact. So thank you very much for your attention. I know this was a lot of information. Hopefully you found it useful. Please do forget. Well, can you forget to evaluate? And the rest of you, please remember to evaluate. Thank you very much.